Okay, so in this video I want to talk about, let's continue our topic on hydrostatic pressure and the forces that result from it, but also I need to talk about Riemann sums. One thing I didn't talk about so far is that I told you we'd have the scenario of a flat vertical surface that's in contact with fluid somehow, either whether it's the side of a tank or it's the plate itself is submerged in a fluid, whatever it may be. And I said, well, here's how you set it up. You impose the y-axis, you make some measurements, and then this integral will tell you what the total force on that object resulting from fluid pressure is. Weight density times depth times width times dy. Okay? I never explained why that integral would work, but it would not be right at all if we were in calculus and I didn't tell you why the integral worked. Okay, so I'll do that. And the integral is really just a limit of a Riemann sum. Okay, so in order for me to tell you how and why that is, let's take this example. Suppose that this is the wall of a dam for a lake. Okay, so there's like a reservoir of water behind this wall containing a lake. In the lake water, we'll say it has a density of 62.5 pounds per cubic foot. Okay. What makes this different than other problems I've done in the videos is the sides of this are irregular. They're not a line or a circle. They're kind of wiggly, and so finding a function to calculate the width across is not going to be practical. Okay, if this was a perfectly straight line, that'd be a different story, but it's not. Okay, I don't really have a name for this shape. I don't have an equation for the shape. Okay, so let's say that we, as we've done before, impose the y-axis on this shape, and that we go about trying to measure the fluid force on this dam like this. Okay, I make some measurements. Maybe some engineers go out to the dam and they say, well, with respect to this being the y-axis, at position 100 feet, the depth is 50 feet, right? I mean, let's say the water goes all the way to the top, so at 100 feet, that's 50 feet below. And then the width, say, is measured to be 1,400 feet. And at position y is 50. The depth is 100 feet, but the width is 800 feet. So it's like we measure 1,400 feet across and then maybe 800 feet across, okay? All right, so they're just measurements so far. And then when y is 0, like down here at the very bottom of the dam, let's say that the engineers measure it to be 650 feet across. Okay, so these are just measurements. All right. Okay, now, so how does that help us estimate the fluid force on the dam? Like, how can we use these measurements? We could do something like this. Now, there are many, many variations on what I'm about to show you, but what I'm showing you gets across the basic idea. Okay, here's what the measurements did for us. So here's the dam again, and then there's like the lake behind it. All right, full of water. All right, that picture or that image becomes like this. These measurements. 1,400, 800, 650. I could imagine that imposes these rectangular plates on the dam. Like that by those measurements on the table, this is 1,400 feet across. Okay, and there's a rectangle. And then this one's 800 feet across. And this one's 650 feet across. And let me call those rectangle 1, rectangle 2, rectangle 3. Okay, now that's what the measurements do for us. But again, if it's my goal to find the fluid force, or in this case to estimate the fluid force on the dam, then here's what I can do with that. Okay, now notice, rectangle 1 is at a depth of 50 feet. Rectangle 2 is at a depth of 100 feet, which is 50 and another 50. And rectangle 3 is at a depth of 150 feet, which is 50 and 50 and 50. Okay? Now, the pressure on each rectangle, okay? When I do this, I'm going to assume that I'm calculating the pressure based on the deepest point. Okay, so what's the deepest point on this first rectangle? It would be 50 feet. So if I take 50 times 62.5, you calculate pressure in a fluid as 62.5 times depth, all right? Given if the fluid's water and that's the weight density, then I can say, well, the pressure on that plate or this rectangle is 3125 pounds per square feet. Now, real quick, let's pause. Is that accurate? Well, that's not really accurate. Why not? Well, because pressure increases with depth. Okay? But for the sake of this Riemann sum, we're going to assume like that we're just chopping things into parts. That there's this plate, and then that's the pressure on it. And then there's the one beneath it, and then the pressure is a little bit different. And then there's the one beneath that, and then the pressure is different for that. But for every one of those rectangles, we're going to look at the deepest point and calculate the pressure as 62.5 times that. And we're going to assume that the pressure is constant across the whole plate, even though it's not, okay? That's the way Riemann sums work. Now, if I then tell you the area of each rectangle, like 1400 by 50, 800 by 50, 650 by 50, then I'll get their areas. And isn't force pressure times area? So if I calculate the pressure on each plate, assuming it's constant everywhere, and then I calculate the area of each plate, and then I multiply them, then I get a rough estimate to the force. Okay? So force being pressure times area, this is what it is on the first rectangle, this is what it is on the second, this is what it is on the third. So on the whole dam, I can add those together and say, well, it's as an approximation, 773,437,500 pounds of pressure or force on the dam. Okay. All right. Now remember, this is a Riemann sum. When I calculate this and add it together to get that really is a Riemann sum. It's only approximation because on one hand, the rectangles don't perfectly cover the dam. They don't fit perfectly. And two, I'm assuming, as I mentioned, constant pressure on each rectangle, even though that's not really true. Okay, but with more measurements, the approximation can improve. Okay, imagine if I made like so many measurements, I could like divide this dam into like 100 different rectangles. They'd all be much smaller. Then both of these problems would disappear. The pressure would still not be constant, but it wouldn't vary as much over the rectangles because they'd be much smaller, so there wouldn't be as much room to vary. And they would also cover the dam better, okay? Maybe you've seen those Riemann sums in Calculus 1 where you find the area under the curve and you assume there's a bunch of rectangles and so on. Well, the more rectangles you have, the better they approximate the area under the curve. Same thing here. It's just that the more measurements we need to really make that number accurate, okay? So if this seems kind of sloppy and if it seems to you like that approximation wouldn't be very good, well, we'll get the idea across, and in practice, the more measurements we start off with, the more truthful and more accurate that number is going to be. In fact, that's all the integral really is, okay? So here's what we just did. The Riemann sum I just did was like this. I took the depth times 62.5 for each rectangle. That was the pressure at that depth. And then I took the measured width. Remember, the engineers measured the width at various points on the dam times delta y. Delta y was 50, okay? That was like the vertical division of my measurements along the dam, okay? And then the measured width times delta y, that was the area. Okay, well, what's pressure times area? Assuming pressure is constant for each rectangle. Well, that would be force. Force is pressure times area. Now, you do this for a bunch of rectangles, you add them all together, and that's a Riemann sum, okay? If delta y goes to 0, if that vertical division for your measurements goes to 0, the Riemann sum becomes the integral. Look how, these two things will always seem so similar. Instead of a finite summation, we're getting an integral. A to B, well, that's the span of our division of measurements vertically in this case. Depth, weight density, width. Instead of delta y dy. Remember, that's how we set up the integral. I said, well, you gotta sketch your problem, put the y-axis on there, get a function that tells you the depth along the y-axis, get one that tells you the width along the y-axis, throw in the weight density, and then do dy. Well, that's because it's from this Riemann sum. That's why the integral took the form that it took when I showed it to you originally and when we started working our problems.